Until now, our discussion has focused on discrete probabilities. Recall that we started with three axioms. First, the probability of an event is never negative. Second, the probability of a whole sample space is 100%. And third, if you take two events and combine them, you can add the probabilities if they are mutually exclusive, which means they do not overlap. Using this information, when probabilities are discrete, then you can compute the probability of an event by adding up probabilities at points. For example, consider the sample space consisting of just the numbers 1, 2, 3, and 4. If you know that the probability of 1 is 0.2 and the probability of 2 is 0.15, then looking at their union, what can you do? Well, we check 1 and 2, and we see that those two sets do not overlap. And so by axiom 3, I can find the probability of the union by adding them. And this gives us 0.35. Now imagine I'm looking at continuous information. Those axioms apply regardless of whether you're looking at something that is discrete or continuous. However, when probabilities are continuous, computing the probability of an event is not as simple as adding up the little pieces. Let's see why. Imagine that you look at the interval from 0 to 2. I choose a value uniformly at random in that range. What is the probability that I pick the number 0.7541893? Well, nobody's going to pick that number. It's basically never going to happen. The probability of that point is 0. You might be imagining, well, but a half is going to happen more often. That's a nice number. But if I'm choosing uniformly at random, it means that every value has the same chance. The number I wrote here that seems bizarre is just as likely as a half to be chosen. So more generally, the probability of any point x is 0. And this is because there are infinitely many values between 0 and 2. They all are equally likely, so the chance of any one point is 1 divided by infinity, or 0. This means that you cannot find the probability of an interval, say 0 to a half, by just adding up the values at points. So we're going to need to take a different approach to studying probabilities when we look at continuous regions instead of discrete things like just a few points. So to get started at this, let's look at the example that was just considered. We have the interval from 0 to 2. I'm going to choose a random point uniformly, meaning every point is equally likely. What is the chance I pick a value from 0 to a half? Well, one way of approaching this is with a picture. Look at the interval from 0 to 2. Notice that 0 to a half, the little blue region, can be copied 4 times, the 4 little marks at the bottom. All of those 4 pieces have the same size. So therefore, 0 to a half occupies 1 out of 4 of all outcomes, or probability is 1/4. However, if I make a modest change, this becomes much trickier. In particular, let's say that instead of every value being equally likely, I'm twice as likely to pick numbers between 1 and 2. Well, because I'm twice as likely to pick numbers between 1 and 2, those last 2 pieces I have in my image are more likely than the first 2. I do not have 4 equal pieces, so the probability is no longer 1/4. What I could do is put some weights on there. I'll put a 1 for the parts that go from 0 to 1, so we have a couple of 1s there. And then the part from 1 to 2 is twice as likely, so I'll fill that in with a 2 at each point. We now have a total of 6, and one of those 6's corresponds to 0 to a half, so the probability is 1/6. This sort of serves as a starting point for a more general approach. Instead of adding up points, we have some kind of weights. In the previous example, you had a weight 1 at the first portion and a weight 2 at the second portion. So more generally, to define this weighting, a probability function on the real numbers is continuous if there is a function, f sub t, such that you can find probabilities on an interval by integrating that function. Integration is the continuous equivalent of adding. So that discrete example where you added up a few points turns into a continuous example where you integrate. This function that we're working with needs a few properties because this is going to be used to find probability. Thinking back to the axioms, axiom 1 said probability is never negative, so the function we integrate should always be positive. Also, axiom 2 said that the probability of your whole sample space is 100%. So the integral over all the real numbers should be 1 for 100%. So let's return to that earlier example. Look at the interval from 0 to 2. Choose a random point uniformly. So in order to define this function f, since all the points from 0 to 2 are equally likely, that function is going to have some constant value. I don't know what it is yet, but the same number should go all the way from 0 to 2 because all those points are equally likely. Nothing else should happen, so 0 everywhere else. How do we find that unknown constant? We'll look up at that property b. It says the integral over all the real numbers gives me a 1, so I can integrate that value c. In particular, before 0 we had nothing, from 0 to 2 we have c, and from 2 to infinity we have nothing. So integrating those three pieces gives me an integral of 0, an integral of c, an integral of 0. Do the integration, plug in the limits, and this integral is 2c. Property b says that the integral will be equal to 1. So 1 equals 2c, and c equals a half. Let's revisit that. When I did that integral, I integrated the 0 parts because I was going from minus infinity to infinity. However, integral of 0 is 0. So when you're doing computations with a continuous probability function, you can also ignore all the zeros. So I could just as well have just taken the integral from 0 to 2. I would still get 2c. It would still equal 1. And so c would still be a half. Now let's revisit the second example we looked at. In the second example, values were twice as likely between 1 and 2. So thinking in terms of this probability function, that means that this f has to be twice as big between 1 and 2. I'm going to spare you the integration. You can go back and check it yourself if you want. But if you integrate this function that takes the value of 1/3 from 0 to 1 and is twice as large from 1 to 2, you will find that integrates out to 1. So this describes a continuous probability function which is twice as likely between 1 and 2. Now, let's go back and use that formula that relates probability in an interval to an integral. Consider the interval from 0 to a half. If I were to draw this visually, we have our sample space from 0 to 2. I care about just that little bit at the start from 0 to a half. The probability function was described by f of t that you see here, recalling that it is twice as likely between 1 and 2. The probability over an interval is found by integrating f. In this case, I'm only looking at values from 0 to a half. All of those values fit in that 1/3 region. So integrate 1/3, 1/3 t, plug in the values, and we come to the conclusion that the probability over this interval is 1/6. We found that answer previously by drawing the interval, breaking it into pieces, and putting weights on each piece. Now we have a method that applies more generally. I don't have to be clever about coming up with a nice construction to break my problem into parts and weight them. I simply need a function f that describes my continuous probabilities, and I integrate it.